All right, it is 2:40 and we have a lot to cover today. So let's get started and then hopefully you can start your weekend. Okay, so what are we talking about today? Well, if you remember last time we started our new module on parsing. And in particular we said, the very technical word that we're using that you probably won't hear very many other places is syntactic analysis. And that essentially means that we are organizing our tokens into structure, finally. So a lot of you had some really good questions about, what happened if you had like 1.1.1 in the tokenizer. And, the tokenizer, tends to actually do okay sometimes with stuff like that, even though it looks very odd to us as programmers. This is where we're going to start to catch those types of errors. And so what are we going to do? Well, we're going to talk a little bit more about derivations, not too much, but we're going to switch into parse trees. And we're going to do a lot of talking about parse trees, and they will be one of our best friends over the next week or so. People mentioned it a little bit last time about precedence and associativity. We're going to talk about how the parse tree encodes those properties, and we're going to go through some examples. So before we get started, we'll do some announcements as always. So homework 1 is due by midnight tonight, so please get that in if you haven't already. And keep in mind that there's no guaranteed help after business hours. So after 5 o'clock, I like to spend my Fridays not on Piazza. So, and the TAs as well. So if you have questions, get them in by then, and we'll do our best to answer them. But yeah, just keep in mind that that's when help kind of ends. And thanks to those who are asking and answering questions on Piazza. I think there's been some good discussions. So that's always a resource for you. Again, don't ask for in-depth homework help. Don't show code. Don't discuss things very deeply. But if you have questions about maybe one test case, and if you have an input string and say what should Alexa do here or something like that, that's okay to discuss. So I think the discussions have been pretty good so far. And then we're going to have homework 2 released by midnight tonight. And you should have enough to get started on it. Again, you'll have enough to kind of get started on part 1, and then there'll be a little bit more for part 2, and then finally part 3. And this homework is, in the past we combined this homework with the one that's going to be your homework 3. So because of that, you're only going to have 1 week to do the second part of the homework, but just keep in mind that it is half of what was an original homework. The reason why we split it in half is in case you need the solutions to this one to do your next one, you don't sort of get hung up on this one too bad. So that'll be released by midnight tonight, and you can start looking at it. It's writing grammars, so probably not too surprising. Okay, any questions about what we got coming up? In that case, let's get started and talk about the quiz. So remember, we were talking about context-free grammars, and those context-free grammars, they had what we called production rules. So if you remember what a production rule consisted of, does a production rule have terminals? Who says yes? Yes, decent number of people. Does it have regular expressions? Nobody. Does it have non-terminals? Yes. And does it have function calls? No. So it looks kind of like code. Remember, we did some of these examples. We're going to use BNF form, which stands for Bacchus Noir form. And these production rules contain a sequence of either non-terminals or terminals. So non-terminals are like your program variables. You, as the grammar writer, can just make as many of them as you want, make sure they have unique names. For example, we have add expr. That could be a non-terminal. And then we define it. A lot of times we'll use : equals. Occasionally, if we just kind of say equals, it should be clear from the context. And then it has terminals. So in class, we're going to be seeing terminals as tokens, which we're going to try to stick to uppercase for tokens. Sometimes in the slides, we'll use string literals. It's not too hard to imagine just pulling this out as a token, like plus. So these are terminals, either strings or tokens. And by convention, and which will probably be required in your homework too, tokens are all uppercase and non-terminals are lowercase. We're going to try to stick to that convention. If there might be mistakes, but we'll do our best. And a production rule is one of these lines. So add expr is a non-terminal, and one of the production rules is num plus num. Now, a non-terminal can have multiple production rules. For example, you could have simple expr that has this first production rule, or it has a choice of the next production rule. It can be num plus num or num times num. So each of these lines is a production rule, and on the left-hand side we have our non-terminals. Okay, here's an interesting question. There are certain patterns that regular expressions can express that context-free grammars cannot express. But it's not really an issue because those patterns don't show up in practice. Who says true? Who says false? A few people. Yeah, so one way, Elliot, it looks like you're indecisive. Okay. One way that you can do this, if you are wondering, and you can do the same thing, if you're thinking about if one programming language is stronger than another, one thing you can do is if you want to compare them, you can say, if context-free grammars are at least as powerful as regular expressions, then anything I can express in a regular expression, I can express as a context-free grammar. And we saw, when we discussed regular expression, there's only 3 operators that we have. We have concatenation, choice, and star. And if we can show how to express those 3 operators in a context-free grammar, then we know that context-free grammars are at least as expressive as regular expressions, right? These are the 3 ingredients that made up regular expressions, and if we can mimic them, then yeah, they were at least as powerful. So concatenation is easy, right? We have a non-terminal, and it can be num plus num. That's just concatenation of strings. Choice is easy as well. We said a non-terminal can be one sequence of operations, or it can be another. That gives us the choice. Now the question is can we build the star operator in context-free grammars? What do people think? Simon's saying yes. How do we do it?
I think if you did expression : equals and then terminal expression and then an or and then just a terminal.
Yeah, I think that's almost exactly what I have. So if you wanted to express a star, that regular expression, if you wanted to express it in BNF, what you do is you could say a star equals the empty string, or nothing, right? Because star can repeat 0 times. Or it matches one character of A followed by a star. And remember, we said one of the reasons, or basically the reason how context-free grammars get its power is through recursion. A star can refer to itself. That's totally fine. And this just allows us to get A repeating 0 or more times. So because we showed that we can handle concatenation, choice, and star as context-free grammars, that's just that we basically have our proof here that context-free grammars are at least as powerful as regular expressions. And it turns out that they're more powerful. You could also do something like this. There's other ways how to do this. This way is a little bit redundant. Okay, let's move on to the next question. We talked a little bit about derivations, and we talked about parse trees a little bit. We're going to talk about them more today. But is it true that a left derivation always produces the same parse tree as a right derivation? Who thinks that's true? Cameron thinks it's true. Does anybody think it's false? A few more people. Okay. Cameron thinks it's true and false. Explain yourself.
So I think I originally answered false to this, and I thought about it some more, and I think the reason why I'm saying both is because if you have like brackets around like a nest or like a certain level of the hierarchy of your code, I think those brackets can then guarantee that you'll get a parse tree that is equivalent to the other one. So I think it depends on whether you're taking into account the things that denote like structure in the code, basically.
Like braces, or maybe in Python white space and stuff like that. Yeah, I think that's a reasonable answer given what we've seen so far, because when you have those white space and when you have braces, it sort of prevents that ambiguous grammar that we saw last time of the if-else. And we're going to see if-else grammars come back up. So yeah, if you use things like that, and we'll talk about other ways how to write your grammar that avoids having different parse trees. Essentially, this question sort of leads into some of the material today. What we want is we want that any derivation, left or right, or if you choose a random order, will give you the same parse tree. If they can give you different parse trees, then we say that that grammar is ambiguous, and we do not want ambiguous grammars. So we're going to talk a little bit more about that, but Cameron's definitely on the right track. And actually, we did get that far in lecture. These slides are from last year when we were moving a bit slower. Okay, and this sort of, again, builds off of what Cameron was saying. Different programming languages make structure more or less explicit. Some of them have parentheses, some of them have braces. Python has white spaces. What do you prefer? Like when you write in your programming languages, like when you write an if statement, do you always use braces, or do you leave the braces out when you don't need them? And like how does it affect you as a programmer? Does anybody have any thoughts on that? Yep.
I just know there's I think it's a Python, like a pseudo interpreter. I don't know. It's Python, and it essentially just adds brackets to Python.
Oh, really?
Like translates it.
Uh-huh.
And like to me, that just seems better. I like the brackets in terms of like organizing my own thoughts in my code, not just for like what the machine can read, but for what I can read.
Yeah. I mean, I really like braces as well, because it really just captures it. So you say, this block of code, and it should stay within here, right? And even if I have an if statement with one statement, you don't need the braces in that case, but I put them anyways. And part of the reason why I put them is in case I want to add to it later, right? Then it's a very easy way how to introduce bugs. But yeah, it's interesting because what we're going to see is those things like that can make the code easier to parse for the machine. But I think as humans, it also makes it easier for us to read. Anybody else have any thoughts on this? Cameron?
I was kind of thinking about how when you're forced to use the tabs and white space in Python for the structure, it enforces, because in C++ you don't have to indent anything.
Right.
And Python's use of that does force you to sort of structure nests properly, so you can't just write code that's all on one column, I guess.
I mean, yeah, in C you can write it all on one line, right? You can just have one line because new lines are ignored. Right. Yeah. Yep.
My big issue with Python with white space and stuff is generally I think it often encourages single line things because it's very hard to break something out into multiple lines.
Mm-hmm.
And it's still parsing because you generally have to then add braces and stuff around it to make sure it all still stays there. It doesn't just, this is another line, it's a different expression.
Yeah.
And I think it causes lines to get very long, and you're on a laptop screen, you can't see the entire line now. Or you have some documentation pulled up on the other part of your screen, you can't see the whole line now.
Yeah.
So I like the 80 character rule line for code.
Okay.
I think Go does a better job of this, where basically there is a standard code format. It still has braces and stuff like that, and doesn't use white space significance, but it has a standard formatting syntax that it does every time you save a file if you're using the LSP.
That sounds cool.
So yeah,
but
it forces you to use that.
yeah, and what I'd say too is there clearly isn't one right answer here, right? Because there's so many different programming languages, and they're good for different things, and people like different things about them. And what's interesting is as we're writing compilers for them, this stuff, should sort of be in our minds, because it's not just what's easy to parse, it's what people want to read, and sort of there's this connection between them, and sometimes there's a relationship between what's easy to read and what's easy to parse, and sometimes there's not. So I think it's worth thinking about. But yeah?
Yeah, I would just say it was interesting you said that you feel like the braces help you to read,
Mm-hmm.
and I know a lot of people are similar, but when I started learning on C++, but my instructor drilled into our heads like, you have to indent by 4 and everything has to be indented, because it is going to be impossible to read anyway if you don't do that.
Right.
So I actually read my ifs and my loops by reading the indents. I never look at the braces.
Interesting.
I found that really interesting. So Python kind of looks the same to other languages to me in that sense.
Yeah. I mean, Python takes it a step further in that they require it, right? So that's almost like the compiler or parser or whatever helping you enforce that rule that you kind of rely on implicitly. Yeah. And so all of the stuff kind of gets handled in the compiler, and these decisions of language design kind of get handled here. I also talked a little bit about S expressions. Has anybody used S expressions? Okay, and S expressions are just very easy to parse, maybe not human readable, but just tons of parentheses. We won't have too many time or we have an example on the next slide, but we won't get into them too much, at least not right now. But we have like all sorts of different choices. You have braces after an if statement. You have parentheses. Maybe you have parentheses to explicitly say precedence. Right here we're saying 6 times 3 goes first. That's what we learned in grade school. But that's an assumption. Maybe somebody who comes from a different planet has a different rule with precedence. And in that case, you'd want to use parentheses to explicitly provide order. When I talk about S expressions look like this in sort of prefix notation. And in this notation, you do times, you do 6 times 3, and then add 5 to that. And I don't find this very human readable. But the thing is there's no question about which one comes first when you write your program like this. So S expressions are actually pretty good at removing all of those assumptions that we relied upon, but they end up maybe not being so easy to kind of look at and understand at a glance. So lots of different decisions here, and they all have their trade-offs. This is the one that we talked about last time. We kind of had a statement, and we said a statement could be an if, then, else, or a statement could be an if, then, or it could be something like an assignment or whatever else. And then what that leads to is if you're trying to parse a program that's like if, then, and then you have an if, then inside, and then you have the else. And the question is does this else match with this if, or the innermost if, or the outermost if? And we kind of saw that question can be expressed as a parse tree. So you have a statement here, and the statement matches if expression then statement. And the question is you could blow up that statement and then have the if then else on the if else on the inner one, or on the kind of the rightmost, or you could parse this a different way. You could have the if or the else match the if on the outside. And so this sort of visually shows where the confusion might happen. And in the grammar that we have right now, both of these parse trees are allowed. And the question is do we care at this point? When we were doing the lexer, we didn't care. The lexer basically said, here's a token, and then my job is done. But at the parser level, we want to start putting meaning into structure. So those trees are actually going to start to encode the meaning of your program. And so the structure that we want is that when you evaluate the tree in the post-order traversal, then we get the meaning of the program. So let's remind ourselves about the post-order traversal. So post-order traversal, there's different types. Hopefully you remember this from your data structures and algorithms, but we have pre-order, in-order, and post-order. Post-order, in my experience, seems to be the one that kind of shows up the most in computer science. But in post-order, you end up going down your left branch, so you visit that one first, then you come up, then you go down your right branch, you visit that one second, and then you evaluate the parent last. And what we're going to see is that this just has a very nice properties, especially when we're evaluating expressions. So again, if we look at these parse trees, and if you try to evaluate them in a post-order traversal, up here, what this one means is that this is just an if statement on expression 1, and then you have your if-else on expression 2. So this if matches that else. Otherwise, you have your if statement on expression 1 matches the else, and then your inner one is just an if on expression 2. Now the question is we've seen some of this, and we're like, this is a problem, and clearly there's a problem with our grammar here, because our grammar allows for both of those parse trees. What is it in C, though? So if I have this program, I essentially have something like this. What does this actually do? So this is kind of a C program. This is a 5-line program, and you all kind of know C. Can you tell me what this does? Like at the end of this program, what is the value of check 0? If check 0 is initialized to 0, x is 1, y is 0. What do people think? I'll let you look at it for a second. And again, this is a 5-line program, so in your careers, you'll be hopefully working on programs that are thousands, if not millions, of lines of code long. So we should be able to handle this. Okay, what are our options? What can check 0 be? Yep. 1 or 0. Yep. So already we've turned this into a true or false. You can basically flip a coin. Is that what your compiler does? Is that what your computer does? Does it flip a coin on this? No. So then, do we think check 0 is going to be 1 or 0 at the end of this? 1. Why do you think that, Jacob?
Without braces, the if statements can only have one thing inside it. So we do if x is 1, so true, pass down to the y.
Okay, so we're here.
If y is false, so you go to the else for y.
So you're saying this else matches this if?
Yes,
You-
because there's no brace surrounding the if x, so x only contains the y. If y is false, then go to the else.
Okay. So I thought with braces, it was just one line, right?
Well, yeah,
So it was just one line.
It is unclear.
No, actually, you're right, Jacob. I'm just so it's not just one line. If you don't have braces, it's not one line. It's one statement, and this is a statement right here. So Jacob's actually right, but you can see how this gets very confusing, especially if we're used to indents. So what I like to do is, when I have a question like that, I just like to go and run it. So this is essentially what we have. And let's compile it. And, a compiler will actually give you a warning here, because this is saying, it's saying add your braces, because this is a confusing thing, as we've seen. But it's still valid. So we can run if else, and we get 1. The reason for that is if we were to put braces, we'd get a brace here, get a brace there, and then let's see. The auto tab in Emacs knows where that should go. Oops, let's see. And that's how it ends up looking. So in C and C++, and I think most languages, they will bind your else to the closest if. So this else gets bound to the closest if. It doesn't go wider than that. And that's a rule that you might have not thought about, but it's going to appear when we start writing grammars. We need to figure out which one we want and how to fix our grammar so that our grammar actually produces the parse tree that we expect. So essentially, we want to produce this parse tree, this that matches the second if to the else. Okay, so what's interesting, and we hinted on this a little bit earlier, but what if you had this in Python? What if you had this exact same program in Python? What would happen?
It wouldn't let you do it.
Yeah, it doesn't let you do it at all. Like, it won't even run. It doesn't parse. So what's nice about Python is they've sort of solved this issue. We can't even run this. It says indentation. So Python forces us to say which one we want. We could do this, or if we play a different game with the tabs, we could do that. But Python forces us as the user to say which one we want. And like I said, there's no right or wrong answer, but I do think this might be a place where Python got things right. Okay. So I think it's always kind of fun when you can find a little program that makes you think about these things. Okay. Any questions on that? This is kind of, yep.
So every expression gets turned into a parse tree, and then that's parsed later and evaluated, or we give it a bunch of tokens, and then that's turned into one giant parse tree.
So what we're going to do is we are going to define a grammar, and that grammar will create a parse tree out of the tokens, and then later on, so if you're doing an interpreter, or like then you will evaluate the parse tree. You will traverse the parse tree and evaluate it. But if you're compiling to a binary, then there's a few more steps that we have to do. And when we evaluate it, rather than actually doing the additions and multiplications, we emit code. We'd emit assembly instructions that do add and multiplication and stuff. So we still have the rest of the quarter to get through that. But we're just going to be making our parse trees for now. Good question. Okay. Let's get into the ambiguous stuff, because we saw how that works with like if and else, but I think this is actually better illustrated with expressions. So what we're going to do is we're going to define a simple expression language. So we have some tokens here. We have our numbers, we have plus, times, then we have left parenthesis and right parenthesis. And our simple grammar is, our expression, again, it's recursive. So I'm going to start off with a base case. Our expression can be a number, or it can be an expression plus an expression. It can be an expression times an expression, or it can be an expression surrounded by parentheses. Hopefully that's not too controversial. And I want us to think about these things in terms of parse trees. So let's draw some parse trees and think about how to derive them. So for example, if we have the input of just 5, well, we have to start with an expression, but then we can just pick this top production rule, and it's a num, 5. So our parse tree in this case is more like a parse stick, but it's still technically a parse tree. If we do something like 5 times 6, we start off with an expression. We have to start off with an expression. But then we can do production rule. Let's see if this is production rule 1, 2, 3. We pick the third one. Then we can get an expression times an expression. And then for each of these expressions, this expression can be a number. This expression can be a number. And again, we can do that post-order traversal. We can say 5 times 6. And that's what we mean here, right? Now, if we have an invalid input, if we had like 5 times 6, what happens is that you just will not be able to build a parse tree. And we're going to talk more about an algorithm to determine this in a bit. But for now, what you'd kind of have to do is you'd say, if I wanted to try to match this, I start off with an expression. There's a time symbol, so I know we have to somehow get that time symbol. So I'm going to apply rule number 3. I'm going to have expression times an expression. But then, in order to get rid of that second times, I would need something like a number and a times, or a times and a number, and I don't have that. So again, we're going to talk about an algorithm to show this, but you can start to think about when you have an invalid input, when you have a syntax error. And this is going to start corresponding more and more to what we think of as valid programs, that you just won't be able to draw a parse tree for it. Okay, so let's get back to some valid parse trees. Okay, so this one's a little bit more complex. It's 1 plus 5 in parentheses times 6. So let's start with our expression. Which production rule do we apply here first? Yeah. The plus one? Times. Okay, yeah. If we zero index, this is the second one. Times one. Why do we do times? Yeah. I think you're thinking along the exact right way. Is if we think about it, this is an expression. This 1 plus 5 is an expression, and then we times that by 6, and that's an expression. And so the times needs to be on the outer, because on the right-hand side here, we're going to get an expression, and that needs to be 6, right? So we get our 6 there, we have our times, and then this expression can be the 1 plus 5. But we need to match that with the parentheses. We need the parentheses to get matched. So that expression is going to be left parenthesis, expression right parenthesis. This one goes down to an expression plus an expression, and then you get 1 and 5 there. So we've built this parse tree. It's a little bit, these parse trees are getting a little bit more interesting. But yeah, we're able to handle stuff like this. Okay, does that make sense to people? Yep.
By the way, those DNF statements, that's what they're called?
Yeah, Bacchus-Nohr. Yep.
Wait, so those are just that's just us writing it in theory land.
Yes, you're absolutely right. This is theory land. We're going to move to algorithms in a couple of lectures, yes. So this is theory land, and this is us as a human deriving this by hand right now. And then, because the algorithms to actually create a parse tree from these get a little bit intense, and so we're going to have to work our way up.
So, just to run me by again, are those rules?
Yeah, so this is a non-terminal, and each line is a production rule. So this is a production rule, expression mapping to a num, or expression mapping to an expression plus an expression, or an expression mapping to an expression times an expression. Each of these choices is a production rule. And each time we expand it, we pick one of the rules to expand it. Yep, and when, right now we only have one non-terminal. That's fine, it just means it's kind of a simple grammar. We can add as many of these non-terminals as we want to make our language more and more, complex but also expressive. Yep, and, so right here we just have all of this taken together is called the grammar. Yep, so this is a simple expression grammar. Okay, let's move on to something else. So, does this parse tree capture the structure that we want? Well, let's do our post-order traversal. In our post-order traversal, we come down to this expression. We do our plus before our multiplication. Is that what we do here?
Yeah.
Yes, we do our plus before our multiplication. So this one looks good. Let's see what happens if we get rid of those parentheses. If we get rid of the parentheses, what should happen first? The multiplication. That's what we kind of learn in grade school. And let's see if that's going to happen. Well, this is a valid parse tree, right? We can do this expression. We can do that times. This is basically the same parse tree as we had before, except I just got rid of the parentheses. And here, the plus is happening first before the times. So that doesn't feel right. What feels a little bit even more strange is without those parentheses, I can actually come up with another parse tree. I can give us the parse tree that we want. I can say, let's match the plus first and then do the times over here. So given this grammar, I can come up with two different parse trees. And if we want the parse trees to have that meaning in them, this one says do the plus first, this one says do the times first. What this means is essentially, given this grammar, this mathematical sentence means two different things. We don't want that in our programs, right? It's bad enough with the bugs that we have to deal with ourselves. But if our programs can start to mean two different things, we don't want that. So let's think about how we can avoid ambiguity. And in particular, this ambiguity is related to precedence, because you do some operators before another. And in this case, we want to do multiplication before plus. So, how we get rid of it? In a lot of modern tools, they will actually just let you specify it. Like we talked about parser generators. They, sometimes some of them will let you just say precedence, and then you can say multiplication is greater than plus, and then it makes your life really easy. But there's a better theoretical way. Well, I don't know if it's better, but there is a theoretical way that I think is really satisfying to encode it into the grammar. So, and it follows what I think of as a fairly simple recipe that I also think is quite elegant. What we need to do is we need to encode precedence in the production rules. And what we're going to do is we're going to introduce one new non-terminal. Remember, non-terminals are like our variables. We can introduce as many as we want. We want one new non-terminal for each level of precedence. And the lowest precedence goes on top, highest precedence goes on the bottom. And so if we have our simple expression grammar, which is plus, star, and parentheses, let's look at that. So I like to draw these in a table at this point. So our lowest precedence, the thing we do last, is plus. So in the table, I'm going to say these operators have the lowest precedence, plus at the top. We're going to call these expressions like we have. And then what we have is an expression can be an expression plus an expression. Now, previously we said, or it could be an expression times an expression or a num. But how we're going to do this is rather than encoding the multiplication here, we're going to say an expression can also be a term. Now, these are just the names that the textbook uses, and maybe if people know a lot of mathematics, I think this corresponds to that as well. But a term will now go down to the next level of the table. And the next level is the next highest precedence, which is multiplication. So multiplication, we're going to call that a term. And a term can be a term times a term, or it can be a factor, because parentheses have higher precedence than multiplication. And then the factor has our left parenthesis expression, because whatever you put in parentheses is going to have highest precedence, and we can loop all the way around, right? If you put something that has an addition inside of the parentheses, it's going to still have highest precedence. So you can do recursion, and you can loop yourself around to the top of the table, but only if you're surrounded by parentheses. So a factor is left parentheses, followed by an expression, followed by a right parenthesis, or the base case of our recursion, or it's a number. Okay? Let's see how this actually looks when we draw a parse tree. So this was a string that was giving us problems, right? 1 plus 5 times 6. Let's think about how we can actually do a parse tree for this. So we start with an expression. And because we start with an expression, we have to pick one of these production rules, first one or second one. So it can be an expression plus an expression or a term. Which one do we pick? Do we have to pick one of them? What do people think? Yeah? Well, so and this will get this. It'll take a second of you staring at parse trees, but we actually want to do the first one, because what happens is when you are higher in the tree, that's where you do the lower precedence, right? Because when you do post-order traversal, when you're lower in the tree, you do those operations first. So lower precedent things happen higher. It's kind of like a mirror to what you might expect. But there's another reason. At some point, we need to match a plus symbol, and if we don't match it here, where else can we match it? Because, if we try to say, oh, let's go for term, well, if we go to a term, then we can match a times, or we can match a factor. And if we go to a factor, it either needs to be a num or it needs to be parentheses. So there's no parentheses here. So if we want to get rid of this plus, if we want to match that plus, we have to pick this first production rule. So we have to match that first one to get rid of plus. There's no other way we can get rid of plus. So then we get two expers. Now, on our right-hand side, we end up getting some pretty long kind of sticks in our parse tree. But this exper goes to a term, goes to a factor, and goes to 1. So now we get 1 plus. Now we need to get the 5 times 6. So this exper goes to a term. From a term, we can do term times term. And then these terms can become factors, and those factors can become nums. Now, like I said, there's no other parse tree we can get from this grammar for this string, because we have to get rid of this plus somehow. And so that plus has to happen at the very beginning. These factors cannot turn back into expers without parentheses, and there's no parentheses here. So this is the only parse tree we can have. Now, the question is does this parse tree encode the meaning that we want? Well, if we do post order, we come down here, we get 1, we see plus, but in order to get our right-hand child, we need to come down here and get the times. We get 5 times 6, which is what we want. That 30 bubbles up here, and then we can do 1 plus 30 and get our 31. So this does encode the meaning that we would like. Does that make sense to everybody? So the key to this approach to remove the ambiguity because of precedence is this table. Now, this table, I think, can actually be pretty powerful. Like, let's try parsing or creating a grammar for regular expressions. Let's say in regular expressions, remember, we have the OR operator. Just to make things a little bit more explicit, let's say concatenation is the dot. Let's say we have the star. And let's say we have parentheses. So remember, we can specify regular expressions, and regular expressions, we can make a grammar for them. So, if we remember, what was the lowest precedence in regular expressions? Yep. Yeah. I think your mirror. Yep. The or. Right. That one happens last, right? You concatenate all your strings and star them, and then you or them. Yep. What's the next one? Anybody remember? Cameron? Concat. So we'll do dot. Remember, I know this isn't normal regular expression, but it's just easier to have an operator for it, so we're holding it there. Okay, the third one? Is it parentheses or star? Jacob? Star. Yep. And then we have parenthesis. So we've basically ordered our operators in terms of precedence. And then what we could do is we could just give them a name. Now, these names, again, they're like variables in a programming language. There's no reason why we couldn't just call this like temp 0, temp 1, temp 2, temp 3. But, it's probably better to be a little bit more descriptive. So we might call this choice, concat, star, and then maybe unit, something like that. Okay, and then all what you really have to do is you just follow that recipe. A choice is a choice. If PowerPoint's not going to auto capitalize it, choice pipe choice, and then the second option for it is what? We just work our way down the table. Concat. Okay, then what would this be? Yeah. Concat. Except instead of pipe, that's the choice operator. We're just going to say dot. Yep. But yep. Yeah, you could probably do something like that. Concat. And the other option is star. Okay, now what are we going to do here? Star looked a little bit different, right? Star is like, you could do something like A star or B star. So how does that work? Yeah?
Would it just translate to unit star and nothing else?
Well, okay, so what you could have is you could have B star star. It's a little bit redundant, but I guess the question is like, do you want to have something like that in your language? We have that choice. We have that power right now. If you had B star star, is that the same thing as B star? Yeah?
In regular expressions, does it do something different, or is it valid?
I think Python, somebody can correct me if I'm wrong. I think Python will get mad at you if you do that. Does somebody want to try it real quick? In the theory of regular expressions, you can write this. It's totally fine. It's just a little bit redundant. So let's stay in sort of theory land. Let's allow this. So what would we do? Yep.
Would it just be star followed by like the star?
Yep. So we'll say star in caps. Yep. Or a unit. Yep. Yep. Yeah, Python gets mad at you. Yes, but according to the theory of regular expressions, it is allowed to do something like that. And I guess Python, that's probably something that you probably don't want to do. So it makes sense that Python gets mad at you. Okay, and then our unit is lpar. And again, if you surround something by parentheses, you restart your precedence, right? You can put a choice inside of parentheses. So L star or lpar choice, rpar, or remember we said the base case of a regular expression is a character. So this is, I don't know, I think this is kind of interesting. We've now defined the language of regular expressions. We've defined a grammar for it in a way that is not ambiguous with respect to precedence. And we thought of, we've had to think about those things. We have this recipe of the table. But yeah, so, behind the scenes in your homework 1 or whenever you do regular expressions, the regular expressions that you write have to be parsed. And there is a grammar like this behind the scenes parsing your regular expressions. It's a little bit strange that we need a parser to parse our regular expressions to build our parser, but at some point it does break this self-referential loop. Yep. Sorry, what was that?
How does the first three operators get to the char base case if they don't have a unit in them?
Well, so we will not be able to accept the empty string here because we at least need one character. But if we have a regular expression that is just a single character, right? Then what we'd do is we'd have the single character. A choice could pick concat could pick star, star could pick unit, unit could pick character. So basically, it's a bit of a journey, and it feels like a long journey just for the simplest regular expression. But what we have encoded here is we've encoded the precedence. So that's sort of the trade-off there. Yep, does that make sense? Okay, good question. Anyone else? Okay, so yeah, essentially I have the solution on the slides as well. What we can do is, if we have an input, let's say we have A concatenated with B or C star, if you have the grammar, and even if you don't remember what the precedence is, you can make a parse tree here. And the parse tree ends up, they get a little bit tall because exactly the question we had earlier, they get tall because every time you want to match a single character, you kind of have to go down these long paths to get down to the character. But yeah, and so, like I said, at some point in your regular expressions, this parse tree is getting made, and it is kind of compiling that to a regular expression matcher. Okay, does anybody know how many levels of precedence C has? So up here we saw regular expressions. We have like 1, 2, 3, 4. Does anybody know how many precedence C has? Anybody have a guess? Yeah, 30. Like 30. Okay. What do you think, Max? 12. Okay. Yep. 8. All right. I think those are all good guesses. I mean, we kind of know that C is crazy. But, those tables that we build, you can just go find documentation. And it turns out that we have 15. So, yeah, about half of what Jacob said, but and double of the 8. So, still seems like a lot. Probably more than I can remember. But yeah, it gets pretty interesting. You can sort of see these operators like plus, plus, and minus, minus. They have super high precedence. The bitwise left and right shift, they have their own precedence level. Stuff that, like I said, I don't keep in my head. But C is a crazy language, and if you want to know the precedence of your operators, you can always Google it and find it here. Yep.
So it says prefix increment and suffix for precedence 1 and 2. So that means like if it is like I plus plus, that would be of a higher precedence than plus plus I.
Yeah. So this is prefix is 2, postfix is 1, and you can go and try to write the craziest programs you can think of to kind of explore those things, but. Yeah, stuff that I don't know. I don't spend my days thinking about, but clearly somebody has. Yeah, so like I said, these tables that we're making, we can go find them for the real languages out there, and it is important. It is important to have explicit precedence. Otherwise, you leave the door open for ambiguity. One question here, though, that I think is kind of interesting is. We still, these tables have, these rows have multiple operators. So, if plus plus and minus minus prefix, or, here we have plus and minus. We have plus and minus up here. Those have the same precedence. So don't we still have ambiguity here? Like, if there's a plus and minus, which one do you do first? And this is this is maybe something you might just do. So you might do it naturally because you've kind of been doing it forever. Yep. Yes, exactly. When things live in the same precedence level, we need to think about associativity. So we're going to talk about that. Let's see, either this time or potentially next time. So yeah, we still need to sort out some ambiguity. And yeah, so let's get started talking about associativity. So if we have some parse trees, so here we've used everything we've learned up until now. We have a simple expression grammar. Here we're going back to plus and multiplication, and we've followed the recipe, and we have this grammar that encodes the precedence. And now if we have something like 2 plus 3 plus 4, we can make a parse tree that looks like that, right? It's a valid parse tree for this grammar and this input. But there's also another parse tree we can make. So we have, again, we're running into this problem where we have 2 parse trees for the same input. Now, I have a question. Does this matter in this example? See, Max is saying no. Why doesn't it matter, Max? It was a big deal last time. Explain a little bit more what you mean by that.
2 plus 3 plus 4 is the same thing as 2 plus in parentheses 3 plus 4, just as a math.
Right. When we're doing math, you could do a 2 plus 3, and then add the result of that to 4. Oops, sorry. Add the result of that to 4. Or you could do 3 plus, PowerPoint's annoying, 3 plus 4, and add the result of that to 2. And it's the same thing, right? So, is this really an issue? What if we had subtraction? Does it matter now? What do people think? Yep, you're saying it matters. Do you want to say why? Yeah, it's not associative. So over here in this parse tree over here, we would do 2 minus 3. 2 minus 3 is negative 1. Minus 4 is negative 5, right? So if we evaluate this, 2 minus 3, you guys have to check me because I'm known for making mistakes here. So minus 5 there. If we do this parse tree, we come over here, we do this minus first. So 3 minus 4 is negative 1. And then 2 minus negative 1 is regular 3, right? So these parse trees now evaluate to different answers. And that's because we're looking at this new operator, subtraction. And so we said it before, there's a difference here between plus and subtraction. Plus is associative, meaning you can do it in whatever order you want. Subtraction is not associative. What other operators do we know that are, well, first off, which ones are associative? Do we have any others that we like? Yep. Yeah, multiplication and addition. They're pretty good for being associative. And then what are the ones that are non-associative? Yep. And division. Yep, that's one that, well, we haven't seen. So yeah, you get this analogy between plus and multiplication, which isn't that surprising, right? Because multiplication is just repeated additions, and division is kind of like repeated subtraction. So, but I want us, and I know the weekend's coming up, but if you have some spare cycles, think about it a little bit. Sometimes it doesn't matter so much, and especially in math, but we have integer arithmetic, integer multiplication. You can test these things. For example, a good test to see if something is associative or not is if you have A, operation B, operation C, and if you just put parentheses in different places, you check to see if you get the same answer. Now, of course, that doesn't really constitute a mathematical proof, but it's always a good kind of back-of-the-hand test. What about floating point arithmetic? Is floating point arithmetic associative? What do people think? You're saying, Simon?
They never are, because there could be rounding from one of the expressions that isn't like makes it the other one not count as much or something like that.
Yeah, floating point is very strange, and I don't know how much time you've all spent with it, but in real, when we think about math in its kind of pure sense, when we go take a math class, multiplication and addition are associative, and it kind of doesn't matter whether you're playing around with integers or real numbers. But computers have to deal with the real world, and so we have a finite bit representation. And it turns out that it does matter the order that you add things together with your floating point numbers. So if these are floating point numbers, even if you have addition and multiplication, they are not considered associative. Yeah, so like I said, I think this is where it gets interesting to think about some of this stuff. I guess the question is is it going to be big errors? Like if you kind of do associativity transformations with floating point numbers, are you going to see like massive errors? Is it going to like blow up your program? What do people think? Max is saying maybe. Yeah?
No, unless like you program it badly, like make a for loop with floating point numbers or something, or like check like restricted quality.
Yeah, and There are some certain, I guess you might call them pathological examples that can really add up and do horrible things with floating point numbers. But for those of you who are interested in certain domains like machine learning, maybe you can tolerate some of those errors of adding things in different order. Maybe some people are interested in graphics, like in video games. That's another domain where you can tolerate some of these small errors that happen. Yeah, did you have a comment?
So if addition and multiplication are not associative for floating point, would it be best practice to code that in for all multiplication and addition, or just treat floating points separately?
Yeah, I think that's an excellent question. Should we just treat floating point differently, or should we just encode some rule for all of them? Yeah. So I'm going to come back to that in 1 second. But did you have a question as well or comment?
No, I was just going to mention, because you were asking about there's programs about that floating point matters. I guess in the rare case, if you have something that has to do with dynamical systems like the weather, if you start with the parameter, I mean, this gets into detail, but
Yeah.
it's just like if you start with a parameter that's 0.01 different from another parameter, then a week later the weather is totally different on the data. But that's like very nuanced.
Yeah, so some domains it matters. Like some domains it matters a lot. Little errors can really accumulate and add up. Other domains, maybe you can get away. Like if you're playing a video game and maybe if a couple of pixels are off, maybe it's for one frame, it might be okay. So yeah, and this is still a conversation and area of research that people are still thinking about. So like I said, I think this is kind of worth spending some time thinking about. So if an operator is not associative, then we define left to right associativity, meaning you read it like you read a sentence in English. You start with your left and you go to the right. So you say 2 minus 3, and then the result of that is minus 4. So basically you have these implicit parentheses that you start from the left and then you go to the right. Do we have any right to left associativity operators? Can anybody think of any of that? Do we have any operators where we kind of start from the right and go to the left? Yeah.
How about like powers, right?
Yeah.
2 to the 4 to the power of 2 or something like that.
Yeah, that's one that not a lot of people think about, but that one does end up being right associative. Any others that people can think about? Jacob?
Finding pointers.
What is it?
Finding pointers, like if you have a pointer to an int, you find the pointer to that int, you find the pointer to that pointer, you find the pointer to that pointer, and so on.
Yes, because you sort of expand that. You go from start on the rightmost side and then go to the left, right? Yes. So, yes. And in fact, you can see that there are some rights to left here. There are some right to left here. One that I sometimes think about is the assignment operator in C. For example, how many of us write something like, x equals y equals 6? It's going to do the y equals 6 there. Y equals 6 returns whatever y is, so 6, and then that happens there. So when you have assignment, although we might not think of it in our mind as being kind of evaluated from right to left, it does end up being evaluated from right to left. If we come over here on the terminal, what we can do is if we go to Python, exponentiation is always the one that I think about as well. So if we do 2 raised to 3 raised to 4, we're going to get some giant number. But the question is if it's left associative, then that will be the same number as doing this, right? We've just put our parentheses in there explicitly. You can see that's much smaller. So exponentiation is actually right associative. So what that means is you do the 3 raised to the 4 first, and then you do 2 raised to the result of that. So yeah, you can always do this test. If you want to know, and if you have a command line, just try running it without parentheses, and then put in the parentheses in the order that you think they should go. Okay. So now we kind of have defined left associative and right associative. And there are more rules that we can apply to our table to enforce some of this associativity. let's actually, I think what we'll do is we'll wait till Monday to get into that, because we only have 5 minutes left. Before we go, though, I want to play around with I want to just do one experiment to show you about floating point and kind of how strange it can be. So let's just have this as a generic function. Let's say it takes in a float x, and let's say it returns a float. Okay. So what we can do is we can do something like return x. So we're not really doing anything here. And we can look at the assembly, and we don't have to look too hard at the assembly. But what I want to try doing is if we do 1.0 plus 2.0 plus x, what we're going to see here is, let's see, and I'm going to do a -03. We are going to get what the compiler is going to do for us, right? And we're going to talk about ways that the compiler does this. I'm over here, I'm doing 2 floating point additions. Somehow we need to add all of these together. What the compiler has realized is hey, I can do 1.0 plus 2.0. And so up here in the assembly, it's giving us a constant. Somehow it's evaluated that the result of that is equal to this number, and it's doing 1 addition. So it's only doing, compilers are pretty smart. It's optimized this, what we wrote in the code, from doing 2 additions to doing 1 addition. If we change this just slightly and say x plus 1.0 plus 2.0, now we get 2 additions. And the reason being is that floating point numbers are not associative, meaning that the compiler needs to do x plus 1.0, and then it needs to add the result of that to 2.0. It needs to do it from left to right, because these numbers in floating point land, you cannot change the order in which you add them up. So just changing our code very simply like that has stopped the compiler from doing some optimizations. Now, if we are living in, let's say we're doing something like machine learning or graphics, there's actually a special flag, fFastMath. I think that's right. And if you do -fFastMath, you're telling the compiler, hey, I know that technically these numbers are not, or these operators are not associative, but this is you giving the compiler permission to say, yeah, there might be a couple of small errors, but I'm going to assume that I can do this floating point number or floating point arithmetic in an associative way, and then we get back our single addition right there. So kind of interesting once you start thinking about this stuff and you start thinking about what compiler optimizations are possible, which ones aren't, and maybe some flags that you can sort of bend the rules with. So I think it's fun to play around with this sort of stuff. All right, with that being said, we have 2 minutes left, but let's call it good for today. So thanks, everybody, and enjoy your weekend, and get your homework in if you haven't.